Hello, class. Today, I'm going to explain the electron charge to mass ratio. This experiment can be explained by classical physics. We don't need any quantum mechanics. Consider a uniform magnetic field that points to the board. And then consider a bunch of electrons that you inject them from the left. What happens? We know that the magnetic field bends the electrons, then they make a full circle. We have seen this in the general physics courses. The radius of this circle is the lowercase r, and the velocity of electrons is v. We know that the magnetic field doesn't do any work on the charged particles. It just bends the charged particles, as you see here. So let's write some equations. We know that the magnetic force is equal to this expression. And again, we know that the centripetal force is equal to this equation. Here, we know that this magnetic force provides the centripetal force. So these two forces are equal, and I can equate them. If you manipulate them, you end up with this equation. The r, the radius of the circle, is equal to momentum of the electron divided by charge of electron multiplied by b. So from this equation, we need this equation for our experiment. From this equation, we see that the r is proportional to v, the velocity of the electrons. If you increase the velocity of electrons, the radius increases. And on the other hand, the r is proportional to the inverse of the magnetic field. It means that if you increase the magnetic field, the radius decreases. So let me continue. This is a tangential velocity here is equal to r angular frequency, and then again I do some calculation and I end up with omega. And omega is equal to 2 pi f. F is the frequency of rotation. So this is our final equation. This frequency that's called the cyclotron frequency is equal to EB divided by 2pme. So you see that this one doesn't depend on the radius. It is why it's called the cyclotron frequency. And the cyclotron names comes from the early accelerators. Let me go one step forward. And these electrons that I showed you here, they are accelerated by an electric field. So, and remember, our final goal is to measure the charge to mass ratio. So let's continue here. We know that the kinetic energy of the electrons that here doesn't change is equal to 1/2 mv squared. And this one is equal to EV. V is the accelerating voltage. Here we have an electron gun that accelerates the electrons, and they give them the final velocity of V. So from here, I can find V in terms of the accelerating voltage and the mass of electrons. So I have, this is the mass of the electron, this is the mass of electron. Let me write it here. So we need this, yeah? Charge to mass. Again, from this equation, I know that is equal to V divided by BR, and I can use V here. I can write that like this. And again, we have another MV here. You can do some manipulation, and you end up with this. This is the final equation, 2 accelerating voltage divided by B squared R squared. So in order to measure the charge to mass ratio, what I need, first of all, I need to measure, or I should know the accelerating voltage. Second, I need to know the magnetic field, and this is a uniform magnetic field. And finally, I need to know the radius of the circles, that the electrons make a circle. This is all about the theory. Let me, at the final step, explain about the Helmholtz coil. Here, I mentioned that we have to produce a uniform magnetic field. In real life, the uniform magnetic field is produced by something that we call it the Helmholtz coil. Helmholtz is the name of one German scientist, and this one can give us the very uniform magnetic field. It's like this. You will see in the experimental setup. We have two coils that are exactly the same, and the same currents flow in both of them. And here, somewhere here, between them, we can have a uniform magnetic field. See? This magnetic field, I'm not going to derive it, I've just mentioned this one here, is equal to this expression. Look at this. N is the number of turns, I is the current, and R, capital R, is the radius of these two coils. In our experimental setup, the number of turns is the 130, is fixed, and the radius is the 158 millimeter. But we can change the current, and mu 0 is the constant, we know that. So again, I can replace this expression here, and I end up with this equation. So it is our, it is our final equation that you need to do your calculation. E over m is equal to 2 times the accelerating voltage divided by this expression. You see here, so in this case, I need to know the accelerating voltage, current that flows through the coils, okay, instead of the magnetic field. So I need to know the current. It's easy to measure the current. And I told you about the R is fixed here. How about the lowercase r? Again, we need to measure it. So you see that we end up with the measurement of 3 parameters: accelerating voltage, current, and radius of the electrons that they move in they are bent. So in the next video, I will explain the experimental setup, and you will see the Helmholtz coils, and I show you how to change the accelerating voltage, how to change the current, and how to measure the radius.